Centripetal Acceleration. Please make sure you are following along in your packet. Pause the video as necessary to make sure you have all the information. Recall that velocity is a vector. Vectors have both a direction and a magnitude. With that in mind, consider a ladybug sitting on a turntable rotating at a constant speed. Is the ladybug accelerating? It would be easy to say, no, constant speed means it isn't speeding up or slowing down. But the direction of the velocity points is changing. So the velocity is changing. There is an acceleration, but not in the direction of the velocity. It always points in a way that turns the object. This can only be directed toward the center of the object's circular path. As this bowling ball moves in a circle, the acceleration is constantly changing to point towards the center of the circle of rotation. This center-seeking acceleration is called a centripetal acceleration. If an object moves in a circle, there is always a centripetal acceleration which is always directed towards the center of the circular path. Centripetal acceleration is affected by the speed of an object and the radius of its circular path. To find the relationship between the speed and the radius and how that affects acceleration, we will first have to change the velocity and keep the radius the same. So if we look at this ladybug as it rotates around this platform, the velocity is increasing, and as the velocity increases and the radius stays the same, the acceleration also increases. So a greater velocity or greater speed means more acceleration. It's not increasing linearly, so it looks more like a quadratic relationship. The centripetal acceleration is quadratically related to the speed of the rotating object. In order to find the effect of the radius on the acceleration, we will need to keep the velocity the same. As we increase the radius, while keeping the velocity or the speed of the rotating object, the spinning object, the same, we notice that the acceleration decreases. However, it does not decrease in a linear fashion. As the radius increases, the acceleration decreases, but the amount at which it decreases also decreases. So I'm inclined to believe this is an inverse relationship. The centripetal acceleration is inversely related to the radius of the rotating object. The centripetal acceleration is inversely related to the radius and quadratically related to the speed of the rotating object. If we combine these two equations, we can rewrite this as a general equation for all accelerations of objects undergoing circular motion. Centripetal acceleration is equal to the speed of the object squared divided by the radius. Remember that centripetal means center-seeking, so the acceleration points towards the center of the circular path.
An 8,000 Newton race car is able to make a left-hand turn due to friction between the tires and the road. It completes the turn with a radius of 42 meters at a constant speed of 30 meters per second. What is the force of friction on the car? Let's start with a force diagram. The problem tells us that the race car has a weight of 8,000 newtons. That means there's a force of gravity downwards by the earth on the car. And that force is 8,000 newtons down, so negative. Then there's a normal force up by the road on the car. The car turns, which means that it changes direction. Because a velocity has both a direction and a magnitude, changing the direction means the velocity changes. This means there's an acceleration. Because this motion is circular, that means the acceleration is centripetal. We know that centripetal accelerations point towards the center, so the center of the turn in this case would be to the left. So our frictional force points to the left by the road on the car. When we look at our force table, we have a force of gravity downwards, so it has no horizontal component. There's a normal force upwards, so there's no horizontal component. And then the force of friction acts to the left, so there's no vertical component. The car doesn't move up or down. There's no vertical motion, so the net force in the y direction is 0 newtons. There is a net force in the horizontal direction, so we don't know what that is. Now this tells us the force of gravity is negative 8,000 newtons. We know that it's negative because it's down. We can find the net force by adding all the forces in the y direction. So 0 equals negative 8,000 plus our normal force, which makes our normal force 8,000 newtons upwards. We can do the same thing in the horizontal direction. There's only one force, so the net force in the x direction is equal to the frictional force. Another way to find the net force is by using Newton's second law. We can write Newton's second law as the net force equals mass times acceleration. However, this acceleration causes circular motion, which makes it a centripetal acceleration. Remember that our centripetal acceleration is equal to the velocity squared, or the speed squared, over the radius. We were given the force of gravity, but we can use that force of gravity equation to figure out the mass. Remember that G is the gravitational field strength, which we can abbreviate as 10 newtons per kilogram. So our mass is 800 kilograms. We're told the constant speed is 30 meters per second, and the radius is 42 meters. At this point, I think we have everything we need in order to figure out the net force. If we do the math, I think we'll find that the net force is equal to negative 17,143 newtons. Because we know that force acts to the left, that should be a negative net force. Because our net force equals the frictional force, this negative 17,143 newtons will also be the frictional force. A pendulum consists of a 4 kilogram stone attached to a 2 meter long rope. As the pendulum swings at the bottom of a circular path, the rope exerts an upward force of 75 newtons on the stone. What is the speed of the stone swinging at the bottom? As always, that starts with a force diagram. We have a force of gravity downwards. We know that the mass is 4 kilograms, so the force of gravity is going to be 40 newtons down. We also know that the rope exerts an upwards force on the rock. It tells us this force is 75 newtons. So this is a good time to check our work. Because this object is undergoing circular motion, the rock swings in a circular path. So we know the direction is changing, which means the net force is not zero. The motion is circular, so there is centripetal acceleration. Centripetal acceleration means the acceleration points towards the center, same as the net force. That means our net force should point upwards, because that's towards the center of the circular motion, which means this force of tension should be larger. Now let's fill out our force table. We have a force of gravity that points downwards, which means there's no horizontal component. We have a tension force that points upwards, which means there's no horizontal component. The net force in the x direction is the sum of all those forces, so if we add up 0 plus 0, we get 0 newtons in the horizontal direction. Now the downwards force of gravity is a negative 40 newtons. The tension force is 75 newtons upwards. Our net force in the y direction is the sum of all the vertical forces. So negative 40 plus 75 equals a net force of 35 newtons in the upwards direction. Now the question is asking us for the speed. If we could figure out the acceleration, we could relate that to the speed using our relationship for centripetal acceleration. To figure out the acceleration, we're going to have to use Newton's second law. Newton's second law states that the acceleration is proportional to the net force and inversely related to the mass. Because this is circular motion, this is a centripetal acceleration. This means that this acceleration is equal to the velocity squared over the radius. We're told the mass is 4 kilograms. The rope is 2 meters long. That becomes our radius. We know the net force is 35 newtons, and we're trying to figure out the velocity. So let's plug in the variables that we know. If we multiply both sides by 2, we find that the velocity squared is equal to 17.5. In order to find the speed, we'll have to take the square root of both sides. This will show us that the velocity, or the speed at the bottom of the circular path, is 4.18 meters per second.